Good afternoon, ladies and gentlemen. My name is Nikolaos Alexopoulos. I'm coming from University of the Aegean, Greece. I will share the session together with Olga Jivkov, that is under the auspices of TC10, Environmentally Assisted Cracking. You have to accept our apologies because our session was full with presentations, but due to logistics and different administrative problems, the presentation just disappeared in this session, and it will continue on the afternoon session straight ahead. So, so what is right now planned to be delivered is the presentation by Mrs. Puyu from University of Manchester, dealing with nickel-based alloys.
Yes.
And Puyu, the floor is yours.
Thank you. Hi, everyone. Good afternoon. I'm Puyu. I'm from University of Manchester and work with my supervisors, Mac, Dirk, and Andrey. And I'm here to present our recent project on the modeling of intergranular cracking of nickel-based alloy 600 using crystal plasticity and cohesive interface method. So some background about our project. Nickel-based alloy has been widely employed as structural material in pressurized water reactor due to its superior mechanical properties. However, it has shown susceptibility to intergranular cracking. And during the past years, many studies has been conducted to study the complexity of the intergranular cracking. However, the mechanics understanding of the factor that increases the stability of alloy 600 is still incomplete. That brings to the aim of our project. And before that, here is some picture about the intergranular cracking of alloy 600 in the PWR reactor. And so that brings to the aim of our project is to improve the understanding of the effect of the material microstructure and the mechanical field of the intergranular cracking susceptibility of nickel-based alloys 600 by combining modeling and experimental programming. So here, we want to represent the real behavior of our 600. Before walking into the simulation, we need to do some realistic finite element structures. One way of obtaining such microstructure detail information is by using 3D EBS-SD. And from the 3D EBS-SD data, we develop a procedure that integrates NAPR for creating finite element method compatible geometry, including grain tessellation, meshing, and cohesive and inserting cohesive elements. And here is an example structure we created with that procedure and that the details about the finite element model. Those grains are colored by grain orientations. With the realistic model, we then proceed to the simulation part, which we want to model in the deformation. By doing that, we're using crystal plasticity finite element method to simulate the material deformation at a single crystal level. And then we expand this into the grain to look at the grain boundary access energy, which is crucial, quite important. It's very important in the simulation of intergranular cracking. And for this, we use cohesive modeling method. And we first study based on the surface energy of nickel alloys. Then we adjust the cohesive property, basically the grain boundary energy based on the grain boundary disorientation. And for our study, our nodal contribution to this field is we account for the triple junction energy, which hasn't been thoroughly studied before, to further refine the grain boundary energy calculation. And with this method, we're trying to address the challenge of varying grain boundary access energy based on the disorientation and the triple line, trying to improve the accuracy of the simulation of the intergranular cracking. So with those 3D EBS-D microstructure, here's the distribution of the disorientation and the triple junction disclination power within that microstructure. With those information, we developed 3 methods to calculate the grain boundary energies. First method is based on the 2 times the surface energy of nickel alloy, which is 2 gamma S, and this method is denoted as GO. For this method, we consider all the grain boundary has the same energy, so it's a baseline approach. And our second method is to assign different cohesive energy based on the disorientation as a grain boundary based on the existing lecture. With this method, we can account for the effect of disorientation as a grain boundaries. And then that's to our novel approach is to integrating the effect of triple line junction into the JD model further to account for the effect of triple junction disclinations. With all the 3 models, we are trying to, as mentioned, to account for the grain boundary excess energy more accurately to better simulate the intergranular cracking. So as our aim is to capture the behavior of alloy 600. So we firstly calibrate the crystal plasticity parameter with the tensile data provided by sponsor Jivkov. And the calibrator used in this simulation is shown in table 1. On the right-hand side, you can see a stress map predicted by the crystal plasticity model, which you can see the stress distribution across the whole microstructure and also the stress variation along the grain boundary and also within the grain boundary, which reflects the effect of the microstructure features. And then we move from crystal plasticity model to the crystal plasticity and cohesive zone modeling. One set of the cohesive parameter we use is listed in table 2. Note that the G is variable, which depends on the 3 methods we just discussed in the previous slide. So here is our simulation result. On the left hand, there's a simulation based on the disorientation angle, and on the right hand is simulation based on the triple junction disclination power. So before looking into the detail of the video, let me talk about the SDG damage parameter. When SDG equal to 0, that means there is no damage in the model in the cohesive element. And when SDG becomes larger than 1, that means damage start to initiate. And when SDG equal to 1, that means fully damage of that element, means the element has been break. So this parameter gives us a opportunity to track how and where the damage initiates and how it propagates. And that's a cohesive energy calculation for the different models. So when we use JD using disorientation, it leads to the crack initiation at the same grain boundary as the GO, which we did consider the disorientation, but at a lower load. And when we turn our attention to the GT model, where we consider the triple line disclination power, I think you notice that the crack initiated earlier. That means it happened at lower load, and it also happened as different grain. This one happened here, and this one happens at different grain boundaries, and it's propagated much quicker. So the key takeaway from this slide is the energy at the triple junction significantly influence the material behavior. Specifically, is that where the damage initiates and how it propagates. And here are the 2 plots to support our discoveries. So this plot is the damage progression at different grain boundaries. As I mentioned, that the damage initiated at different grain boundaries. And for GO and the JD model, they start at the same grain boundary, which is JB542. And for the GT model that involves triple line, it starts as JB621. And not only they start at different grain boundary, they also propagate in different rates. When we look at this figure, we can see that all the 3 models start at the similar string, and the GT model quickly accumulate and reach to the value of 0.6 around the 10% of string. And when we look at this plot, which the damage evaluation in different grain boundaries, the GT model start quite earlier at the very beginning of the simulation, and quickly develops into the value of 1, which means that boundary has been cracked. So from this slide, from those two plots, we can confirm that we can see that the triple line descalation plays use in the crack initiation point and the propagation rate. And this slide is another support for our series. Is a commutation of the damage in the overall in the overall assembly. So for let's say the first plot first. This is a plot that of the damage element, the percentage of the damage element in the overall structures. And we can see that the TG has the quickest failure rate compared to the other two models, which it reaches to the 80% of damaged element in around 10%, around 12% strain. And other two are just been slower, and been the GO, which we did include any disorientation or triple junction, has been the slowest. And when we turn our attention to this one, this is the percentage of the crack elements in the overall assembly, which we can see the GT starts around 8% of the true strain and quickly become failure in around 12% of strain. And for the GD model, which we consider the disorientation, it didn't start until the 24% of the strain, and it also fell quite quickly, but not as quickly as the GT. And for the GO model, which is a baseline model, it didn't fail until very high strain. So the takeaway from here is that the triple line disclination may lead to the damage localization. So the failure starts occurs at high rate and with substantial reduced fraction of damage the surface. So that's our hypothesis about the that's our discover from the simulations, and from those plots and the videos, we can see that the way we considered in our simulation, whether to including disorientation or triple line junction disclination power, has effect of how we assimilate the intergranular cracking. So to check our hypothesis, we conduct an in-situ tensor test with continuum EBSD monitor, which called the TENNIST. So in this test, a specimen is subject to a tensor test until crack, and with the strain applied in the predefined increment, the specimen geometry and how it assembled in this is how it assembled in the machine. So with this machine, we can take image at each predefined strain level. So we can observe the surface change and during surface change in the real time under load. And at each increment, we got continuous SEM image, which we can observe the material deformation and allow us for the substantial digital image correlation test. And also the 2D SD is also taken at the central area. This here is an example, and this is a central area. This map can help us in analyze the grain boundary disorientation, triple line the changes in triple line disclination, and basically the variation in grains. And those experimental data will allow us to observe the grain level deformation process, especially in relation to local strain pattern, grain boundary disorientation, and triple line disclination, and in related to crack initiation points. Here's our, that should be a video. Can you press it? Is a video? Okay. It should be 2 videos to show the changes in the test. I don't know why it's not showing, but yeah, this is our preliminary analysis about the test, which it should show the grain change and grain orientation change during the test. And this map will help us analyze the change in disorientation and triple line disclination, and which are critical for us to test our hypothesis regarding the influence of triple material behavior, especially by disorientation or by triple line disclination, and we can identify the location where the crack initiates. So to conclude, our simulation so far has discovered that grain boundary excess energy, triple disorientation, triple line disclination has play a critical role in the crystal plasticity and cohesive model of the intergranular cracking. Not only the crack initiate, not only the load that need to initiate the damage, and also the damage initiation point and how the damage propagates. So we are now conducting an ongoing experimental study and to validate that hypothesis to check the effect of the grain boundary energy and the triple line disclination on the material behaviors. So if our validation is successful, it should there should be a bar here, by the way. So if our validation is successful, we will expect weather impact on the mesoscale modeling of the polycrystalline material. And even we are aiming to improve our simulation work about this. So thank you for listening.